Welcome back to the third video in higher order thinking. Today's topic is decimal fractions and these weird things called p-adic numbers. So a brief history is Simon Stevens, born in 1548 in Belgium, died 1620, age 71, 72-ish, he was the inventor of decimal fractions. Probably invented the decimal point as well, the whole notation and all. And he was the guy that gave us these arithmetics we teach to do decimal arithmetic instead of fractions. As a consequence, we get these p-adic numbers later on by other researchers refining his work because there's kind of shortcomings to it, as we'll see. Decimal fractions, some facts you already probably know, is to be a decimal fraction or a fraction is it would be represented as either a terminating decimal expansion, like 1/4 is 0.25, or a periodical one where it doesn't terminate ever, it goes on forever for lengthwise, but it has a period. Like in the case of 1/11, you have 0.09090909 forever and ever and ever. If it doesn't fall into one of those categories, if it goes on forever and never repeats, and that is a harder thing, and those are the irrational numbers. And rational numbers are usually not covered in topics until you get into much higher levels, like in high school. Math exposes the square root of 2 and how you handle some of the irrational arithmetic. In elementary and middle schools, we teach students how to add, subtract, multiply, and divide decimal fractions. Usually after we've taught them fractions, how to add, subtract, multiply, and divide fractions, because it's one of the rather more harder concepts, or probably the hardest concept in arithmetic to grasp, that of working with decimal numbers and decimal fractions and how to actually do arithmetic with these things. And for good reason, because it wasn't a complete theory up until the 19th and 20th century. We didn't have a complete theory for it. So let's see why the reason and what the problem is, because we're all used to doing decimal fractions or decimal numbers no problem. We whip them off and stuff. But we only consider certain special cases of decimal fractions to work with. And we're always taught how to handle those particular cases, but we never taught all fractions, how to do all fractions in decimal fractions. Examples of decimal fraction, which we have no problem doing, is this one. If we convert 1/4 to decimal, we get 0.25, a terminating decimal fraction. So it's no problem to set up and, multiply any number by it, or add or divide or subtract any number by it. We just have to keep track of the decimal point that we teach people and moving the decimal point accordingly when we're doing such arithmetic. However, this is the warning part. What happens if we want to work with something, say, like 1/3 as a decimal fraction? The problem is, in the former problem, which we had no problem with, is it was a fraction that gave rise to a terminating decimal expansion. But 1/3 is the other side. It's the fraction, it's the decimal expansions that are not terminating ever. It goes on for infinity, but repeats forever. So that's still a fraction, and we know how to handle 1/3 in fraction form, numerator 1, denominator 3. We know how the properties and rules to add, multiply, divide, and subtract fractions. But if we want to do it in decimal form, how do we go about that? Where do we line up things? And where do we even start with the multiplication, addition, subtraction, division procedure? So we have these conflicts with the decimal arithmetic theory, not when they're terminating decimal expansions, but when we have decimal expansions that are periodical and non-terminating. That last special case where they're not terminating, that's where we're lacking a theory. And Steven was aware that he was trying to complete this theory of decimal arithmetic, but that was his problem. He was never successful and never got a chance to complete the theory. It took a long time after Steven's, the 1500s, all the way up until the 1900s, into the 20th century. It was a long process. That's the question we're going to go and try to seek what happened. As you know, the more math, it took a long time before we had this problem hashed out. But the solution was always to convert over to fractions. As we tell our students in elementary, middle school, and even high school and above, we just have no problem just converting the decimal expansion to a fraction form and then solving the problem. That's a totally valid way to go. But for mathematicians, they like a complete theory and stuff. So the quest to complete the theory of decimal arithmetic, what happened with this guy. And he was born in 1861. He was 71 when he died, and he found this solution, this great solution, and it was this thing we called p-adic numbers. His solution was the invention of these things called p-adic numbers. Now, decimal representation in base 10 of a fraction can be represented like this, in sigma notation, where k goes from either 0, starts at 0, or at some integer above 0 to infinity. That gets the actual decimal part representation of a number. But he considered, well, what happens if we did the opposite? We did this representation, where in our case, we're going to say p equals 10 in our case. We're going from I equals k to infinity, where k can be 0 or above, any integer above, and we're going to infinity. But now we're going the opposite way. We're not going down the decimal we're not going to the right of the decimal point. We're going to the left of the decimal point with this representation. Now, this representation, if you know from a geometric series point of view, or from a point of view of convergency of a series, it doesn't converge. If you took it to infinity and your base was p equals 10, it would be infinity. So it makes no sense trying to, in modern sense, trying to compute this. This sum is divergent. However, p-adic representations assign a number to this representation. And this number is kind of like the inverse of our decimal expansions and stuff, to some extent, loosely. So let's see an example of all this. And the example I'm going to give you is, suppose we wanted to multiply this 0.3333 on forever and ever and ever, and we weren't aware of 0.3333 was 1/3, and we wanted to multiply by 9. Well, how would we do it? Well, the first thing that he came up with is, let us take a 10-adic number construction, say this number, where now the actual decimal point has finite amount of terms on the right side, mainly just 0, just indicating that there's no terms on that side for this particular example, and 3 goes on forever to the left of the decimal point. Now, if we do this arithmetic that times it by 1 minus 3, we get it equal to 3. And so this weird p-adic number in base 10 is equal to 3. And if we reverse that, flip that, or reverse that number to read the other way around, we get the inverse of it, of 0.3333 equals 3. It's kind of like a weird thing where we can swap stuff and get the inverses and stuff for this particular example. I mean, it gets more complicated, but this is just a simple example to make you aware that of this stuff. And so when you have 0.333 times 9, it's really the inverse of 3, which we know the inverse of 3 is 1 over 3, and 9 times 1 over 3 is just 3. We didn't need to calculate out what 0.3333 equals in fraction form. Even though this is a simple example, you could easily convert that by multiplying, by doing the multiplication by 10 trick minus, the number and so forth, and convert it over, which most would do. But this is a very cool and inventive way of doing it, and it completes kind of the side of decimal arithmetic. Now we have a complete theory for the decimal expansions that are periodic but go on forever. So it's a completion, and the reason why we call it p-adic is that the p stands for the base we're using. Now, intuitively, we're always over 10-adic because p is always 10 because we're in decimal base. We're in base 10 always working it. That's our most common or intuitive manner to work in, base 10. But some people like base 2 or base 16, and in that case the completion of base 2 or base 16 are the 2-adic numbers and the 16-adic numbers, we would call them, and they complete those base systems. Now p-adic in general would complete the p-ary base system. So for example, check it out, see if you can do this one for your. It's more challenging and requires you to research a little bit more into how I'm doing this kind of p-adic kind of weird arithmetic to actually complete this this story of this final chapter in decimal expansions, and see if you can do the 3-adic value of 1/5, which 1/5 in decimals is 0.220, but we want it in base 3, and we want the 3-adic of it and stuff. So the 3-adic of it is shown below, and I hope this was kind of neat and stuff, and now you're aware that the theory of decimals we teach isn't a complete theory. It took many centuries before we were able to get a complete theory, and this complete theory relies on the invention of p-adic numbers. Thanks for watching, and enjoy it. I hope you enjoyed.